Hello everyone, my name is Ronita Bose. I am currently a senior in the Department of Electrical and Electronics Engineering at the University at Buffalo, and I'm going to talk very briefly about the performance degradation of SRAM cells due to NBTI effects. So what is NBTI? NBTI stands for negative bias temperature instability. It is an effect which only affects p-channel MOSFET transistors. It would almost be incomplete if I don't mention PBTI effects. PBTI effects go hand in hand with NBTI effects. As you would have already guessed, PBTI stands for positive bias temperature instability and is only seen in NMOS transistors. As you can tell, NBTI and PBTI go hand in hand in SRAM cells. Now this brings me into the discussion of these degradation effects in an SRAM cell. An SRAM cell, as I mentioned, is made up of a pull-up network consisting of PMOS transistors and a pull-down network consisting of NMOS transistors. Now this is true given any type of SRAM cell, be it 4T, 5T, or 6T. So why does NBTI affect the SRAM cell? Now, as I mentioned, the SRAM cell, the fundamental building blocks of the cell are PMOS and NMOS transistors. So any degradation which is affecting the building blocks at the device parameter level is bound to affect the SRAM performance and reliability. I'm going to mainly focus on the effects of NBTI, and wherever possible, if absolutely essential, I will also couple it with the discussion of PBTI. Now, when we think of SRAM operation, we mainly think about three things: standby or hold mode, read operation, and write operation. I'll first talk about the standby mode or the hold mode. During the standby mode, the SRAM circuit is non-functional. The supply voltage still stays on, but ideally the SRAM cell should not be consuming any power at this stage as it is not performing any function. But it is the standby stage which helps us determine the leakage power losses of the SRAM cell, which we will shortly talk about. Now, during the standby mode, the access transistors which connect the cross-coupled inverters to the word line and the bit line are cut off. Now, as they are cut off, PBTI and NBTI completely get hold of one of the pull-up transistors and one of the pull-down transistors in the SRAM cell. At this point, when there is nothing else to control the SRAM but the degradation effects, it might seem highly unrealistic, but to be honest, NBTI and PBTI during the standby mode have the potential of keeping the SRAM cell stuck in the standby mode for an indefinite number of years. Now, the SRAM read operation. PBTI effect impacts both the cell read reliability, by which I mean the read stability, and the read delay. But NBTI principally affects the read stability. What do we mean by read stability? By read stability, I mean that it would be highly undesirable if during my read operation, the data in the SRAM cell flips. The worse the degradation effect, the higher possibility of this happening during my read operation. However, although it may seem very surprising, there is a positive aspect of NBTI in one area of SRAM performance, and that is the write ability or the write margin. Write margin is defined by the ratio of the current carrying capabilities of the access transistors to the pull-up network. At this point, NBTI has already weakened the pull-up network by decreasing the current carrying capability. This increases my ratio, thereby increasing my write margin. As you can tell at this point, we can see that there exists a trade-off between the read stability and the right margin of the SRAM cell, and we cannot achieve a very good performance in both at the same time. Making one better will definitely make the other one worse. So the SRAM cell operates at a happy medium between these two for optimal performance. A very important feature of the SRAM cell, which is affected by NBTI and also PBTI definitely, would be the cell SNM. SNM stands for static noise margin. It determines how much noise margin or voltage noise is needed to flip the state of the SRAM cell during normal cell operations like read or hold. As I mentioned earlier, the smaller the SNM, the more easy it would be to flip the cell during the read or hold operation. And I can tie this in with my read stability discussion, where I said that it would be highly undesirable if the state of the cell flips during the read operation. The more degraded the SNM, the faster the data flip during the read operation. If you look at SNM voltage curves, it essentially looks like a butterfly curve, and that is what it is called, SNM butterfly curve. The worse the NBTI effect, the more narrow and degraded this butterfly curve gets. Another very important aspect of NBTI degradation is its effect on leakage current. Leakage power loss is one of the fundamental power losses which we get during an SRAM cell operation. As I mentioned earlier, leakage current is measured when the cell is going through the standby mode, because only then leakage current flows, and the only way of detecting that is when we know there is no other current flowing through the SRAM cell in that ideal operation. The cell has no reason to consume any power at this point, because as I mentioned earlier, it is not performing any read operation or write operation at this point. The cell is essentially idle during the hold or standby mode. Now, this leakage current can be divided into three type of leakage currents: the junction tunneling current, the subthreshold current, and the gate leakage current. Of these three types of leakage currents, the one which is affected by NBTI effect would be the subthreshold current. As you can see, the subthreshold current is exponentially related to the threshold voltage. One of the fundamental aspects of NBTI effect is how NBTI causes voltage threshold drift in the SRAM cell. So if the threshold voltage of the cell is drifting, the subthreshold current, which is exponentially related to that voltage, will also be drifting, which means an unpredictable power loss for the SRAM cell. At this point, I would like to summarize NBTI effects. NBTI effect is caused when a negative bias is applied to the gate of the PMOS transistor. By negative bias, I mean a negative voltage is applied to the gate of the PMOS transistor. This increases the gate threshold voltage, decreases the oxide layer capacitance of the gate, and decreases drain current. As drain current decreases, the speed of the PMOS transistor decreases, because speed of the transistor is dictated by its current carrying capability, and the lower this capability, the lower the speed. And as SRAM performance is dictated by PMOS performance, the speed of the SRAM also degrades. The read stability of the SRAM also degrades, as we saw in the earlier slides. However, the write margin increases. So to summarize, NBTI effect has a positive and a negative effect in the context of SRAM cells. As we saw, The negative effect would be the read stability, and the positive effect would be the right margin of the cell. Ongoing research tries to attain the happy balance between this positive and negative effect. There is research going on to try to reduce the effect of NBTI effect in SRAM cells, but it is very difficult to do so because it fundamentally affects the parameters of the device. And as miniaturization of semiconductor devices for higher capability, higher speed, better performance has become a craze, semiconductor devices are being made to be manufactured smaller and smaller. And this causes non-uniform voltage scaling for the devices. And as the device itself gets smaller, it is given the current technology and the limitation of the current technology, it gets more and more difficult to track down these defects in the nanoscale levels. That is all. I would like to thank Dr. Praveen Madhuri for providing constant help and support during the course of this project, and Thomas for his valuable help and time during the course of this project. Thank you very much.